Hey kids, it's time to do limits and continuity again, just like we did in single variable calculus, right? But we're going to take a look at limits involving functions of more than one variable. So we're kind of moving along those space curves and those shapes in 3D and figuring out if we have a limit that exists. And just like in single variable calculus, if you know continuity, you know limit, right? So it's just plugging and chugging if you have continuity. So obviously we're going to be exploring things without continuity. So, but before, again, remember that when we did limits in single variable, we talked about the overall limit existing if we bump bellies. Those of you that had me for calculus remember bumping bellies, right? Which means the right hand limit is equal to the left hand limit. For example, when you have some kind of continuous function, I don't care where you are on that function, right? If I have some number here, a, I'm not asking about the actual function value at a, right? The function value is right here, f of a, but I'm talking about as you approach a from the left and as you approach a from the right, the corresponding range walkers that have these big bellies, right? The range walkers are walking along the curve, and if they bump bellies, and the reason I make a big deal about the bellies is because even if there was a hole here, even if I didn't have discontinuity, I would still have a limit because their feet would not step on the hole, but their big bellies would touch over the hole. So if you have a removable discontinuity or you have continuity, the limit as x approaches a from the right and left is equal to the function value at a. F of a will equal the limit if you have a hole or a removable discontinuity, or of course if you have continuity. So hopefully you remember the places where you had limit issues. So you had some kind of piecewise function maybe, right? That limit does not exist at a, because as you approach a from the left, the range walker's over here at this level, but as you approach a from the right, the range walker is at a different level. So since the left level does not, or the right in this case, the right level does not equal the left level, the overall limit would not exist. But do you remember there were some other situations where we had continuity, but we still did not have a limit? Right? When there was a corner, because the slopes from the left did not equal the slopes from the right. When there was a cusp, right? There's no unique tangent line I can draw there. When there's a vertical tangent, right? I actually have continuity, but I have an instantaneous place of vertical tangency, and the derivative, right, which is the slope of a vertical line, does not exist numerically. So we're going to try to extend this idea of when does a limit exist to more than two dimensions. And in two dimensions, I only had two hands to worry about, two range walkers. Do they bump bellies, right, from the right and the left? Right? There's only two paths that you can take in two dimensions. There's only two paths. To the point A, I could only come, right, to my function here. To reach this point, I could only come from the left or from the right. That's the only path these people had to get to f of a, or near f of a. However, if you have three dimensions, right? If you have three dimensions, and again, this is going to be a pathetic drawing, but and I have some surface up there in the z-plane, right? Here's my surface, and I have some point here. that came from a certain x and a certain y that you plugged into the function, and it took you up to this surface, right? So the problem is, how many paths are there to that point? There's a whole bunch, right? As a matter of fact, there's infinite paths of ways I could get to this point, right? There could be some kind of space curve, right? Take me all the way through, to get to here. There's an infinite number of paths. So how can I possibly investigate the limit as x approaches that point P? I can't say from the right, from the left, from diagonal, you're right? I mean, what the heck? What the hee-haw? What am I going to do? Well, what we're actually going to do is learn a technique where we are going to try particular paths, because all it takes, just like in 2-dimension, right? What happened is, if the limit as x approached a from the right did not equal the limit as x approached a from the left, you concluded that the overall limit did not exist. So what we're going to do is try a couple of paths and cross our fingers and really, really hope that we get different values. Because if we get different limits with 2 paths, we can say the overall limit does not exist. All we need is 2. So I'm going to teach you a way that for most of the problems we're going to be dealing with limits the number of tries, because you certainly can't do an infinite amount of tries. So again, here's another representation of, oh my gosh, to get to this point in 3-space, I didn't even draw it in 3-space, I drew it in 2-space, right? How many ways you can get to the point is devastating. So how are we going to do this? There's the notation. What is the limit as xy approaches AB of my function in terms of xy? And sometimes I write that, right? So what AB is the point I'm after, right? 2, 1, 4, 7. Now, if you can step 1, just like in single variable calculus, step 1, if this is continuous, if whatever function you have is continuous, then you're just plugging and chugging. So a couple of your homework problems are going to say, where is this function in 2 variables continuous? And what you're supposed to do is just look and hopefully recognize, oh, there's no issues anywhere. It's continuous everywhere. Oh, there's an ln, so I got to figure out right in the expression, right? You're not doing any limit work there. You're just investigating and looking at the function overall and trying to find out. Just kind of sort of like looking at domain, right? But if you do have continuity, when I ask you to evaluate the limit, you plug in A for X, B for Y, and be done. So in order for the overall limit to exist, though, all the paths have to have the same value. So our goal, what we're going to do, all of this verbiage up here says that after step 1, remember step 1 was plug and chug. Step 2, do you get 0 over 0, right? Your indeterminate form. If the function isn't defined there, it's not defined there. So duh, you don't have a limit. But the issue is if you have 0 over 0. So if I have 0 over 0, what we're going to do is we're going to examine a couple of straight paths. We're not going to worry about all these curvy paths. We're going to worry about we're going to investigate a couple of straight paths to a point. And we're going to investigate a horizontal path, a vertical path, and then a diagonal path. And if we must, we'll do something beyond there. So we're going to choose to investigate a horizontal path. where y is always equal to 0. Then we're going to choose a vertical path where x is always 0. And if those two limits are different, the limit does not exist. If those two limits are the same, I'm going to investigate a diagonal path where x is equal to y, right? I might have to do a couple of stranger paths, but let me tell you, the strangest I'm going to get is like x squared or x cubed, right? That's as far as we're going to go. Okay, again, technically you'd have to check a bunch of infinite ones, but that's to prove the limit exists. You're going to be given problems really where you're going to end up showing that the limit does not exist because of the paths that you choose, 2 of them are not going to be the same value. So, firstly, I need to know about continuity. And as I said, some of your later homework problems at the end are asking you about where is this this function in 2 variables continuous? And you're just expected to look at that and rationalize your way through it with your prerequisite knowledge. Some things that you got to watch out for. Right? We've been dealing with this for a long time. What's the domain? I can't divide by 0. I can't take the square or even roots of negative numbers. I can't take logs of 0 or negative numbers. And then my other thing, like tangent, I know where to work out, watch out if I've got a tangent expression and blah, blah, blah. So look at this. This looks devastating. Pull this out at parties. People will be so impressed. They're like, oh my God, you must be so smart. But what do I have here? Squared, a first, a product of 2 first degrees, and cosine. Every single combinations of continuous functions are continuous. So all I have to do here is plug and chug. I am plugging 2 in for x, -1 in for z, 1 for y, and evaluating. Right? Bam. -14, done and done. Plug and chug. However, what if there are continuity issues? Firstly, in these multidimensional problems, as the chances are your limit is not going to exist, right? If you have a continuity issue, so many things have to go right in order to make continuity happen that the chances are your limit does not exist, right? Because remember, if there's continuity issues, you're just talking about is there going to be a removable, which means can I factor and cancel, right? That's rarely going to happen with these complicated functions in our XYZ plane. If you're able to evaluate limits along different paths and get a different limit, then your overall limit does not exist. So here's our example. So the first thing I notice is they're asking me for the limit as I go to 0, 0, the origin. And I look at that expression, I see division, and I see, hey, I can't divide by 0. What makes the denominator equal to 0? It's 0, 0. And not only that, but the numerator is also 0. So I get 0 over 0. So plugging in, step 1, boo, tried that first. I got 0 over 0. So that leads me to 3 choices to start off with. Horizontal path, vertical path, diagonal path. So by doing this, I am reducing the problem to a calculus 1 problem, right? Do you see what I've done here? So I'm changing the problem and saying I'm going to look at the limit as x varies, but y is constantly 0 as I approach 0, 0. So I take the original expression and I replace y with 0. When I do that in simplify, I get a new expression, 0. So now, what is the limit of x whenever y is equal to 0 as I approach 0, 0 of the function 0? What is that limit? Well, right, the derivative of the limit of a constant is that same constant. So my limit is 0. So this was me trying the horizontal path. Next, I'm going to try the vertical path. So notice for the vertical path, I am going to hold x constant. For my vertical path, hold x constant and hold it constantly 0. Replace all the x's with, excuse me, zeros, and I get to the same place. The limit of a constant is that constant. Now, in reality, if I was doing this problem, I would have pretty easily seen that both the horizontal and vertical path would give me 0. So I really would have only tried one and said, well, they're going to give me the same thing. And remember, my goal, what I want, right? My goal is two different limits. I got the same one here, so it hasn't helped. So now let me try the diagonal path. Gosh. It doesn't matter which one, right? If I'm going to choose, I'm going to choose my old y equals x. So notice I'm letting x vary, but I'm making y constantly be x. So I went to each y and replaced every y with x. And I got x to the fourth over 4x to the fourth. The x to the fourth canceled out, and I was left with 1/4. What is the limit of a constant? I took two different paths to the origin. I don't know what this thing looks like, but there were two different paths to the origin, and on either the horizontal or vertical path, I approached 0, but on the diagonal path, I approached 1/4. Therefore, the limit does not exist. Okay? Remember, your attempt or your path has to go through the point in question. I can't just choose random paths. So when I was looking at, right, y equals 0 goes through the point 0, 0. The line x equals 0 goes through the point 0, 0. The line y equals x goes through the point 0, 0. So here is a picture of that shape. Where did I have that picture? Here it is. So I had no idea what that thing looked like, right? Isn't that kind of cool though? But look, right, you can see some, right, it's kind of hard to see though what's actually going on. So what I did first was, there's the path. I looked at the limit holding x constantly 0 going through the point 0, 0. I held x constant and kind of walked along there, and I bumped at 0. Then I turned that one off and I went on the y path. And when I went on the y path and walked from the left and the right, I bumped at 0. But when I went on the diagonal plane here, and I walked along at the origin, right? And it's kind of hard to tell here. I don't know with my scale, but when I walked along y equals x, I approached this level of 1/4. This is a height of 1/4 here. So the overall limit did not exist. Right? I bumped bellies from the right to the left, from the up, the down, if you will. But when I went diagonally, I ended up here. Not bumping bellies. All right, let's try this one. I wanted to show this one because the hint to this one sometimes, again, as you do more of these, you start to see patterns, right? So I can pretty quickly see here that my horizontal, right, and vertical are both going to give me 0. Can you see that? If I do, right, first I plug and chug, and I do get 0 over 0. So I'm going to try my paths. Hold y constant. So my numerator becomes 0, right? Because y squared, this is going to be 0, and my denominator becomes x to the 4th. Simplify that, it is 0. So what is the limit of the constant 0? That limit is 0. And I hope you can see the same thing would happen if I put in x, right? If I held the other one constant. So both of those limits are going to be 0. What happens then? My next one is my diagonal path. So my diagonal path, I'm going to hold y to constantly be whatever x is. And I'm going to write it like this. Right? Because what do I get now? Do you remember some of this from some of this manipulation? Right, here's algebra 1. That's going to reduce, right, and just give me 3x squared. But notice what I have here. I can write this as sine x over x times sine x over x, right, with a 3 in the denominator. And do you remember this? I mean, it's either L'Hopital's or it is just that pattern that you remember, that as long as you're going towards 0, which I am, right, x is 0, and then y is the same as x, which is 0. So remember, this limit was 1. This limit was 1. And the product of limits is the limit of the products. So in this case, I got 1/3, which does not equal 0. Therefore, the limit does not exist. Woohoo! Right, so I typed a bunch of this stuff. I typed up this out, right? This part here. I got to this place, and I had to apply the limit of this expression, right? I didn't, unlike the other ones, right? And I kind of got a little bit lazy with those other expressions, right? I ended up with this expression that I had to take the limit of. In those previous problems, when I simplified, I got to a constant, and taking the limit of a constant equaled the constant. I actually had to apply limit knowledge here, right, after I did algebra. Now, I wanted to show you an alternative trick. Like, you don't have to use x. Sometimes maybe my algebra is a little nicer, right? I mean, I wouldn't say necessarily this, but I just wanted to show you that as long as you go through the point 0, 0, I can make this anything, right? I chose a steeper diagonal path, and I got a different level, but that's okay, because remember what it doesn't, I could have then done these two, Instead of doing horizontal, I could have done 2 diagonal paths, right? I could have done diagonal path 1 versus diagonal path 2. As long as I show that limit, I could have said the limit does not exist. All right, how about this one? So notice what happens here, right? If I want to try, again, I plug and chug and I get 0 over 0. If I do the horizontal path, again, this reduces to 0 over x to the 6th, which the algebra reduces to 0. The limit of the constant 0 is 0. That's going to happen too for the horizontal, right, for the vertical as well. So what happens when I try my diagonal? What do I do with that? Well, I can factor an x squared out, right? Whoops. No, you're right. Silly me. And then what's that limit? I plug in, right, when I'm plugging in 0. Again, I get 0. There we go. Now, instead of just for kicks, let's pretend I wanted to use the path y equals x cubed, right? Remember, my goal is to just get a different path. So I got 0 when I did my horizontal, right? If you do your horizontal path, my first attempts are horizontal path, vertical path, diagonal path. But all of these generated 0. They all generated the same. So that wasn't helpful. So here's another trick. Well, let me not make it exactly straight, right? So I picked x cubed. And again, that's just experience. You could try x squared too. But notice what I noticed what happened. I made sure that my powers got high enough to cancel out. That's what I did. So that I ended up with something that wasn't 0. And once I have two limits that are not the same, I can say the limit does not exist. All right, that's it for now. And I will see you on Friday. Take care.